Welcome to this session. This is a session on jumping into modeling with differential equations. And I'm very pleased to introduce Maila Hallare from Norfolk State University. And she's going to be talking about Laplace meets Tesla, differential equation class confrontation. She has been very active in symbiotic activities and a contributor, and we're pleased to have her at this conference. So take it away.
Thank you, Brian. Laplace meets Tesla in the differential equations class. My name is Maila Hallare. I am from the Department of Mathematics, Norfolk State University. Thank you again to Symbiotic Expo 22. Thank you, Brian, for inviting me. Thank you, everyone, for being here. I pushed too much. Okay. Tesla's ambition of wirelessly transmitting electricity using radio frequency was never realized. Now, more than 100 years after Tesla's experiments, wireless transmission of electricity via magnetic induction is currently used in a humble household electronic, the wireless toothbrush. The wireless toothbrush is one of many household applications of a two-coil wireless power transfer. From now on, I'll call it WPT. In this talk, I would like to present a simple mathematical model of this wireless power transfer via magnetic induction. The system consists of two second-order differential equations coupled by a mutual inductance. Then we will use Laplace transform methods to solve the resulting system because the resulting system is linear. And then we will show how this topic may be embedded in the differential equations class, technologically supported by a free online circuit simulation software, and then numerically investigated further by some spreadsheet data fitting. So let me start with some information about Laplace and Tesla. Well, they don't really need introduction, but Pierre-Simon Laplace was a French mathematician. He contributed a lot to engineering, physics, of course, mathematics. He formulated Laplace's equation, and we know that the solutions, for example, of the Laplace equation gave rise to harmonic analysis, and many other things. For our students, the first time they hear of Laplace is when they learn about Laplace transforms. And in my university, that would be around the 10th week of a 15-week semester in differential equations. On the other hand, Nikola Tesla, he was born about 30 years after Laplace died, and Nikola Tesla was a Serbian-American. I was able to watch a PBS show about Nikola Tesla, and it was really interesting because Nikola Tesla was the son of an Orthodox priest and a homemaker, and his father is actually also a published poet, and his mother was very creative, and Nikola Tesla said that he got his creative and inventive spirit from his homemaking mom, because his mom apparently would make some little gadgets around the house to make things life easy. And so, as we can see here, they did not meet in their lifetimes, but in a differential equations course, they meet. So that is the hook of my talk. Okay, so with Laplace transform, we know that it is a transform mapping scalar functions to scalar functions via this improper integral with the kernel e to the negative st, where of course s is greater than 0. And we will see that later again in my presentation. Well, Tesla was a very good inventor. He did many things, but here I highlight two of them. On the left-hand side, you see a patent that I found, of course, online of his electrical transformer. I choose this picture because you will see later that it is quite similar to the WPT model that I will present. On the right-hand side, you see here a picture of the Warden Cliff Tower, because at that time, Nikola Tesla wanted to compete with Guglielmo Marconi, because at that time, Marconi was becoming famous due to his invention of radiography. And so Tesla's dream was to transmit power. Okay, this tower was in New York, and he wanted to transmit power, not just in New York, but actually across the Atlantic Ocean. Unfortunately, due to funding problems, his dream did not happen. Okay, so anyway, I learned this from my engineering collaborator. Basically, wireless power transfer means many things. But it is broadly classified into two: the so-called radiative far-field wireless power transfer and radiative near-field wireless power transfer, which is then naturally classified into two: capacitive and inductive coupling. What we are going to look at today is just a special kind, the one that says inductive power transfer. Okay, so as I've said, I like this application because students can relate to wireless power transfer because they see it in everyday lives. For example, the humble electric toothbrush. So how does it work? So basically, well, this toothbrush is clean. In a wireless electric toothbrush, we have the charging base connected to the electric power, and then we have also the toothbrush. So let me this is a schematic of what's going on. So here we have the power source in red. The charging base is connected to the power source, and when it's time to put some energy into the electric toothbrush, we put the toothbrush on top of the charging base. And so I would tell my students, if you open up the charging base, then you will see the so-called transmitting coil. In engineering parlance, it's called source. And then in the bottom of the electric toothbrush, you will see the so-called receiving coil, or sometimes called the drain. So of course, when you want to use your toothbrush, while you're using your toothbrush, you don't want your toothbrush to be physically connected by a cable or a wire to the electric circuit, right? And so electricity is, power is being transferred from the charging base to the actual toothbrush via magnetic inductance every time we put the electric toothbrush on top of the charging base. Okay, and so since our goal is to make a model of this wireless power transfer, let's look at a schematic, an equivalent circuit of wireless power transfer. What I have here is a very, very simple model for the setup. Okay, so on the left-hand side, you can think of this as the charging base. Okay, as you can see, this is just a simple LRC circuit. L inductor, R resistor, C capacitor. And this symbol here is our voltage or power source. On the right-hand side, this would correspond to the actual electric toothbrush. This is called the receiving or the receiver or secondary coil. And when the electric toothbrush is in contact with the charging base, then power is wirelessly transferred from the primary coil on the left to the secondary coil on the right. And that happens through magnetic inductance, represented by this M. Okay, so for now, every time I reach this part of the lecture in my classes, so I can see that I already lost some of my students. And so what I did was, so I will stop sharing now. And I would like to share something that I found that I think is quite useful. So I will pin myself, if it is okay, and then I will reverse my camera because I want to share this thing that I found online that I think is quite effective in really convincing my students that this is really fun. Okay, so what I have here is an actual transmitting coil of a wireless power transfer and its corresponding receiving coil or receiver. Okay, so as you can see, the receiver has an output. This LED bulb here, currently it's turned off because there is no power. Okay, so the idea, of course, of wireless power transfer is that when the inductor of the transmitter and the inductor of the receiver are put in contact. So when I put this on top of that, I hope you see that. Yay! That LED bulb light up. Yep. And usually at this time when I do this in class, I would hear some applause, okay, because they really love this demonstration. And so let me now sit and, okay, so I will stop video and then I will now change my camera again to front and then share my screen. Well, if you're interested, that small wireless power transfer system is only about $12, and you can find, if you're interested, I can give you a link to where I found it. Okay, so are you seeing my screen now, my PowerPoint again?
There you go.
Okay, great. Okay, so let's go back to our equivalent circuit of wireless power transfer. Presentation. Okay, so now let's go to the equations. After having convinced my students that they can see this in real life and we are able to study this from a mathematical perspective, let's do the deriving of the model. When deriving the model, I do it in two ways. The first way is what I call a hand waving method, depending on how I was able to introduce LRC in the previous chapter in our textbook. I do this hand waving method. So basically, as we have seen earlier, the transmitting coil is an LRC circuit. And being an LRC circuit, it is represented by a second order differential equation, linear with constant coefficients. And since it is connected to the voltage source, okay, we have a non-homogeneous side. Okay, it cannot be a direct current, otherwise the right-hand side will be zero, the derivative would be zero. So this is a non-homogeneous equation. Now the right-hand side, or the receiving coil, the receiving coil is also an LRC circuit, second order, constant, linear, and homogeneous. Okay, now, of course, when they are in contact with each other, now we finally have a system. Once they are in contact as a system, there would be this so-called coupling, and the coupling will be via the magnetic inductance M, okay? Because this is an inductance, then that extra term will be a second order derivative in the current. So here in the first equation, we will simply add this term here, M times the second derivative of I2 for the transmitting coil equation on top. And then you will add M times the second derivative of I1 to the second equation, which corresponds to the receiver circuit. So this is the coupling that happens between our two equations. Now, okay, now, how do we derive the model using so-called fundamental principles? Well, as you can tell, we need to have the so-called Kirchhoff's voltage law. Okay, using the Kirchhoff's voltage law on the left-hand side, which says that the sum of all the voltages around any closed loop in a circuit must be equal to zero. And so on the left-hand side, we will have voltage. We will have negative V1 because we're going towards that direction. Voltage plus voltage across the resistor, plus voltage across the inductor, plus voltage across the capacitor, and of course voltage due to this mutual inductance. And that's where we get this first equation. Analogously, for the receiving circuit, we will have voltage across the resistor, voltage across the capacitor, voltage across the inductor. Okay, I think I forgot to mention earlier that once I have shown them this thing here, students become curious about many things and they ask a lot of questions. And this is where beautiful inquiry-based learning discussions start. Maybe I'll do that later after my presentation. Okay, so anyway, once we have set up these KVL equations, okay, we will now use some results. For example, using the fact that voltage across the resistor is resistor times the current, and the voltage across an inductor is the inductor times the derivative of the current. Now, these equations from the previous page becomes like this. So this is voltage across the resistor, R times I, and this would be voltage across the inductor, L times I prime. And remember, this is also inductor. So we have Mi2 prime and Mi1 prime respectively for the first and second equations. Okay, one last thing to change and we will be almost done. So notice here that we only need to look at the voltage across the capacitor. Now the voltage across the capacitor is given by this relationship. The derivative of the voltage across the capacitor is 1 over C times I. So from the previous page, what we will do is solve for VC1 and VC2 respectively from each of the equation and then differentiate. Okay, now once we have done that, then we plug in this result regarding voltage across the capacitor. And I hope you can see by this time that we now get our system of equations, which looks like this. Okay. So this is our system of second order differential equations, constant coefficients, one homogeneous, one non-homogeneous. So now let's proceed to solving the system via Laplace transform. Okay, I find that using the Laplace transform in solving the system is most effective when teaching the students this part, because I tried using the other methods like methods of undetermined coefficients, or variation of parameters. I just lose them. And I will show you why Laplace transform would be the way to go. So assuming some simple initial conditions, okay, we take the Laplace of the first equation, take the Laplace of the second equation, then the corresponding system will be given by this system, this matrix equation. Okay, so here, because we have a second derivative in I1, first derivative in I1 here, and then we have our I1, and that's why on the first row, first component, I have L1 S squared plus R1 is the coefficient times S plus 1 over C1. And then here, this, because this is M times the second derivative of I2, using the Laplace, then that will account for this term here, first row, second column, MS squared. Okay, and then in the end, they will use the students will have to use the Kramer's rule, for example, to solve for I1 of S and I2 of S. Okay, so using Kramer's rule, this will be the result. Okay, which is still not that bad when one does this computation by hand. And then, of course, finally, the last step would be to take the inverse Laplace. Okay, now once you have taken the inverse Laplace, then we will have the forms. Okay, I might have deleted that slide. Okay, now I would like to convince you why this is a great example. Aside from engaging the students right from the start because of the beautiful applications, normally in the textbook, when we teach them about second order differential equation systems, and the examples are usually first order, a system of first order equations. Okay, in the textbook, the typical example is the example of a double pendulum for a system of two second order differential equations. However, for this particular example, there are two things that I hope will convince you that WPT is a better example. Number one, this double pendulum application requires that we need to do a first order approximation on the sign, okay? Because there will be sign terms here due to the oscillations, okay? And secondly, the students just don't like this example, okay? Now, let me do what did I have? Yes. Now, let me show you a nice example of WPT in terms of classwork. So with these specific values for the parameter, so here I have L1 is 1 Henry, the resistor is 2 omega, the capacitor is 1 farad, and so on and so forth. We plug this into our formulas that we have derived, right? And I have chosen these values because these values will give rise to forms of the solution that can still be solved by hand. Okay, because as you know, the challenge at this point is that will the students be able to take the inverse Laplace, right? Because in the end, you will have a fourth order in the bottom. So for this particular values, yes, they are still able to do this by hand. So in the end, once they have computed that, then, now this is the reason why I said Laplace would be a great choice for teaching this, because well, some students who are very good in computing inverse Laplace will be able to get through all the way, or we can also tell them that there is a software that will help them compute inverse Laplace quickly, right? Because many of them get lost with computing the partial fraction decomposition, and then you ask them, okay, look at this table, but with this software, then they will be able to find the answers right away, okay? And then of course, through to since this will be introduced in class, then maybe one can use Desmos.com to produce the graph, okay? So using the wireless power transfer to supplement lectures on Laplace transform is really a great example. Now, I would also like to show that when teaching this example, what another helpful software would be a free online software called multisim.com. Okay, so in multisim, it's quite fun because you will just drag and drop the passive and active components that you need in your circuits. Okay, so for this particular WPT, I created this simple circuit. Moreover, using using the online circuit simulator, which is free, would be good because for other values of the parameters, they are just not really very easy to do by hand. But this free online circuit simulator will be able to give us the solutions. Okay, so with these, for example, here with these special values for the capacitor, 13.77, PF, and so on and so forth, then the solutions would be like this. So if it is okay, I will stop sharing my screen. If you want, I can give you a, oh, can you also share the Laplace side? Of course, that's what I want to do right now. Thank you for asking, Kate. In the chat box, let me show you, or let me copy and paste the, okay, so in the chat box, you should be able to get a link to the multisim simulator for our for our WPT. So let me share my screen because I have already clicked on that link. Sorry. Oh, there you go. Share screen. Share screen. Okay. So if you click on the link, yes, thank you, Victoria. If you click on the link that I shared in the screen, you will get something like this. Multisim requires a little bit of learning, but it's not that bad, at least for us mathematicians. Well, I did have some help from some of my engineering friends, but it's not that bad. So when you open the circuit, well, let me just say why. Because your circuit sometimes will complain, oh, this needs a ground. Okay, there will be some guidelines for multisim if there are some components that you were not able to put in there, but I am sure you'll get by. So when you click on open circuit, yes, there are modeling scenarios using multisim. Yes, a lot. Okay, so now I will click on that triangle button. Now I tell the students, okay, this circuit simulator is telling us that electricity is now going through our system. So now I will stop, and then you can click on grapher. Okay, wow, that is a lot. We don't need all of that. So what you can do is, for example, 350 microseconds. That's a lot. Let me change that to 500 nanoseconds. Okay, there you go. Okay, so here, one of there are two graphs because there are two unknowns: the current on the transmitting circuit and the current on the receiving circuit. One of them I set to be blue, one of them I set to be green. And you can actually see that from how you can see that from the picture. Anyway, so here the students can see the oscillation of the oscillating properties of the current function. Okay, I will stop sharing again. I'm sorry, this will be the last time. Then I will go back to my PowerPoint. Okay. Okay. Yes, finally, what I would like to do is from multisim. Okay, from multisim, actually, you can download your data. Once you have downloaded your data and save it as an Excel file, for example. So let me share my screen. Okay, you can download your data from multisim, and this would be a great way to teach about parameter estimation and data fitting. So when you download your data from multisim, what you would get would be these data here, A, B, C, the columns A, B, and C. And then from there, because we are able to find the closed form solutions of our WPT system, maybe you can do that in class using, for example, a variation of parameters or method of undetermined coefficients. Since we know the exact or closed form solution, then we can do a simple data fitting. For example, my favorite is Excel. Well, I also like Julia, but Excel is great because from a student's perspective, they can see right away the changes in the values. And so, for example, after doing a simple data fitting and a least squares regression, this would be the graph of one of the currents. Okay, let me stop here and thank you so much for your attention, and I will not pin myself.
Well, thank you very much, Maila. That was rich, to say the least, but I think your suggestion that avoiding the linearization in the pendulum and sticking with the real things might make it interesting. We always get concerned about circuits. I mean, students sometimes get a little bit leery, but if you give them the basic laws like you did and a demo,
Yes.
You can be very convincing with them.
Yeah.
So if you have other questions, we have a minute or so for them. Anybody want to put something in the chat or raise their hand and voice?
Well, while I'm waiting for the questions, let me just say that when I use this, okay, you can send me an email if you want to know where I got this. When I use this, the students actually, just by showing this to class, I tell them what you're holding right now is a differential equation. This is another differential equation. Put them together, it's a system. And then it started their curiosity. I mean, I had questions like, why are the coil wrapped up in a circle? There is actually an engineering explanation for that. And then they would say, what are those other little things in the circuit? Well, I would say, well, honestly, I do not know. But we can see that there's like in this example, for example, there's more than one capacitor. And then I say, oh, that's actually a good idea for research. What are the things that engineers put into the circuit in order to achieve the purpose?